AI has a big problem, and if you work with Cursor or Cloud Code, you'll already be very familiar with it. Let me describe it like this. In the movie Anchorman, the film's protagonist, Ron Burgundy, is this arrogant and idiotic yet lovable character who's a well-known and respected anchorman in the city of San Diego. He has this known quirk where he'll read whatever is on the teleprompter. This eventually gets him into trouble when he tells the city to go do something to itself that the populace doesn't appreciate very much. Now, AI is kind of like this, but instead of a media network dictating what goes onto the teleprompter, the AI itself plays both roles, that of teleprompter text generator, as well as the presenter to you, the user. And just like Mr. Burgundy, sometimes AI says some wild and untrue things. Things like MCP servers, Cursor rules, skills, CloudMD files have been set up to help mitigate this by giving the model the right context at the right time. But as you're probably aware, it can be maddeningly frustrating when the AI just seems to completely forget everything you were just talking about. For this reason, I've become obsessed with the topic of information retrieval, and more recently, its godfather, a man from the 4th century BC known as Callimachus, who's widely regarded as the West's first bibliographer, creating an indexing system that libraries in one form or another have used ever since. In this video, we're going to learn about that system and how it influences a state-of-the-art innovation released in 2018 known as UMAP, Uniform Manifold Approximation and Projection for Dimensionality Reduction, that tackles the same problems that Callimachus was tackling, but at much greater scales and in ingenious ways. And by the end of this, I hope that you can take some real-world use cases for how to visualize complex data, as well as just being awe-inspired by the types of problems that humans are capable of solving. But if you're new here, my name is Justin, and this channel is dedicated to exposing the art in data science through history and other things. So please consider subscribing if you want YouTube to recommend you future videos as I post them. Now let's get started. So there's this very specific connection between Hellenistic Greece and our day. They were a culture obsessed with new information. At the close of the 4th century BC, this obsession had taken hold especially firmly in the city of Alexandria, who didn't have centuries of existence to lean on when comparing its intellectual and artistic resume against older Greek cities such as Athens. And as a result, after the death of Alexander the Great, one of his most trusted generals, King Ptolemy Soter, became king of Macedonia, which is modern-day northern Africa. Eager to prove himself the true successor of Alexander, he implemented a policy known as universal collection, where ships that entered Alexandria's ports would be searched for any scrolls, and when found, they would be copied, the originals would be kept in Alexandrian archives, and the copies would be returned to the owner. This quickly led to a massive influx in new information that's not so dissimilar from what we've experienced in the internet age. But it also created a problem. The sheer volume made it hard to find the right scroll at the right time. As with any problem, society eventually produces the individuals with the drive and the vision to be able to solve it. And that individual in Alexandria was Callimachus. Now, Callimachus was born to a noble family in Cyrene, which is modern-day Libya, but he wanted to move to the big city of Alexandria to make a name for himself. While he initially found work as a school teacher, he had his sights set higher on the city's intellectual hub, the Library of Alexandria. Now, the library was a marvel because in addition to being the first public library, using quotes there because it was mainly only accessible to the city's intellectual elites, it was also a dumping ground for the cream of the crop from that universal collection policy discussed earlier. Now, this would have acted as a natural filter, but even so, the volume was suffocating, with the total number of scrolls in possession at the time of Callimachus of around 120,000. Imagine keeping track of that many rolled up documents without a computer and no retrieval system. Now, Callimachus eventually worked his way into a position at the library through effectively the ancient Macedonian version of going viral, in that he published poems praising King Ptolemy II and his wife, which gained widespread notoriety for their brevity, which was a new concept for a people accustomed to gauging the quality of literature by its length. Think of the Odyssey. Callimachus instead showed a disdain for length's sake, even being quoted as saying, "A big book is a big evil." He believed it a pure art to express deep emotion and meaning in as few words as possible. Now, perhaps it was this same disdain for the overwhelm of verbosity that led Callimachus to want to organize the Library of Alexandria. He eventually developed an indexing system known as the Pinakes, with which he cataloged the library and separated the information from the retrieval mechanism to access it. Like mentioned before, this makes Callimachus the West's first bibliographer, and for his contributions, he was loved for centuries after, becoming particularly idolized by great Roman thinkers such as Ovid, Horace, Virgil, and Proprietus, the latter of which considering himself publicly at one point the Roman Callimachus. Now, while these men in particular likely idolized Callimachus more for his combination of brevity and depth, to me as a data professional, I'm particularly awe-inspired by the Pinakes, and what a labor of love that must have been. If you've ever had to bucket data by hand, you'll empathize. Pinakes, which is Greek for tables or tablets, was a massive undertaking. Before them, if you wanted to learn or read about a specific topic, you just had to start unrolling scrolls and reading them. And where Callimachus began was to partition the library into categories. Some of what we know from later reference and fragments were poetry, history, philosophy, oratory, law, and miscellanea. But he also logged metadata for each scroll, including the author's name, biological provenance, the title, the first line of the scroll known as the incipit, and the total line count of the scroll. And the final result was a massive 120 volume reference doc that effectively cataloged the entire Library of Alexandria, which effectively represented the entirety of the Greek literary world at the time. But it goes even deeper than that. Picture what this would have looked like in practice. Now, Callimachus clearly didn't work alone. And while he's credited as being the architect of this system, the library employed, using the word loosely in certain cases, a vast workforce of people, from scribes to slaves to professional copyists to subject matter experts such as astronomers and physicians. Some would have undoubtedly just been employed to count the number of lines in each scroll, while others would have been tasked with finding the right shelf for the right scroll. Would this scroll that used poetry to describe a certain history go on the poetry shelf or the history shelf? It could only occupy one space. That required a familiarization with each topic and a tedious, repetitive decision-making process that would have had to have been repeated tens of thousands of times. This process took years, and it didn't even conclude during Callimachus' lifetime. And as the count of scrolls continued to climb to an eventual peak of 400,000, the work never ceased. Now, the modern observer might be tempted to look at that manual, repetitive tedium and think it unrewarding and old-fashioned. Today, when we ask something of ChatGPT or Google, it can be easy to take for granted the hundreds of thousands of people who dedicated their lives, sometimes against their will, to gathering and organizing knowledge. But the fact remains that we're only able to access almost any information that we want at the blink of an eye because of all of these people dedicating all of that tedious effort over thousands of years, and because of innovations within those analog systems from brilliant minds like Callimachus. Now let's fast forward to just a few years ago. Similar to ancient Alexandria, in the mid-2010s, almost 2 decades into the wake of the dot-com boom, we were similarly struggling with this massive influx of new information. And many people were searching for solutions to make this unending sea of data more digestible and searchable. And one such approach was dimensionality reduction, which is conceptually identical to what Callimachus did with the Pinakes. Take a highly diverse mountain of text and organize it into indexes and sections, and suddenly it's not so scary. The modern problem was that the scale of the dimensions of the data had surpassed any previous limits. One off-cited example is gene sequencing. Single-cell RNA sequencing data has 20,000 genes per cell. That is a lot of columns per row. But what if you could remove the dimensions of the data without losing key features or the essence of the data? Just like the Pinakes, suddenly the problem becomes manageable. And data scientists have made several important breakthroughs in dimensionality reduction in the early 2000s. Geoffrey Hinton, who's become quite famous lately, being known as the godfather of AI, developed with the help of Lorenz van der Marten a dimensionality reduction algorithm known as T-SNE, T-Distributed Stochastic Neighbor Embedding. Another well-known innovation that you might be familiar with is known as PCA, or Principal Component Analysis. But all of them to date had their trade-offs that made them unfit for working with large-scale complex data. For example, PCA struggles if the relationships in your data are not similar. If something increases exponentially relative to increases in something else, PCA will struggle to capture that. Take real estate values and distance to city center, for example, with the values increasing exponentially the closer you get to the city center. The PCA algorithm would struggle to chart that. T-SNE, on the other hand, is great with nonlinear relationships, but it struggles as the data starts to scale up. Once you get above 500 dimensions or so, T-SNE becomes prohibitively slow. And due to its use of probabilities, it actually gives meaningfully different results each run. This was the reality in 2018 when a brilliant mathematician named Leland McInnes, together with computer scientists John Healy and James Melville, released a paper that solved this problem in a new and fascinating way. This was UMAP, Uniform Manifold Approximation and Projection for Dimensionality Reduction. But in order to understand it, you first need to understand the concept of manifolds. And perhaps the most interesting thing about UMAP is that McInnes started from pure mathematical theory, to solve this very messy real-world problem. So often breakthroughs in science, especially data science, happen by brute force testing and tweaking of parameters until you get an aha moment. And then theorists spend years backing into the data to prove why it works. UMAP was a rare instance of the inverse of that. McInnes used category theory in a branch of math dealing with stretching, bending, and otherwise manipulating geometric shapes known as topology as the basis for the framework around data relationships. And this framework revolves around the idea of manifolds. And the best way that I found to understand manifolds is to look at something called the Swiss roll example. The best way that I've found to understand what a manifold is to think of a sheet of paper. You have a blue dot at one end and a red dot at the other. Then if you roll it up, you see that the dots are almost touching each other. If you then were to try to measure the distance between the dots, distance in this case being a measurement of similarity, they might measure a couple of millimeters apart. This type of distance is known as the Euclidean distance. And it normally works as a measurement of similarity, but not here. Why? Because this piece of paper represents a manifold or a bending plane which exists between a higher dimensional space, in this case a three-dimensional space. When it's flat, it's a simple two-dimensional plane. Once you roll it up into a three-dimensional space, the Euclidean distance breaks down because it tries to cut through the empty air between the layers. In other words, the only way to find the true distance within the manifold's universe is to unroll the paper and use a ruler to measure the distance from dot to dot. This is known as the geodesic distance, as opposed to the Euclidean distance, which just tried to poke a hole straight through the paper to find the distance between the two. But why is this important? Because in reality, the data is never random. And when you're trying to study complex, high-dimensional data, you'll find that it only occupies a small area within that latent space. For example, I'm in a room that's 10 feet by 12 feet by 9 feet. But if I want to know the distance between these two dots on the paper, like I showed in my example, it does me little good to study the areas up near the corner of the room because the data I care about lives within this manifold. So that's the only thing that I need to focus on to find the relationships I'm trying to find. Here's a more intuitive example. Imagine you're trying to study commercial airline flight patterns across the Atlantic Ocean. In that case, would you waste your time studying the area under the water? No, of course not. The data you're looking for lives on imaginary lines arcing across the skies from one coast to the other. Manifold learning helps you to isolate to studying just those areas where the data relationships actually live. And UMAP takes those high dimensional relationships and boils them down to just 2 dimensions so you can put them on a chart. But so far we've only constrained ourselves to 3-dimensional data because it's hard to visualize anything beyond that. But what if your data is higher than 3 dimensions? What about that single cell RNA data with 20,000 genes per cell that we talked about earlier? Trying to measure relationships between rows with that many columns sprouts something called the curse of dimensionality, which is basically 2 things. One is the space grows exponentially relative to the number of dimensions in your data. Think about how much the space grows just from going the 2D floor at my feet to the entire 3D room. That's just increasing by 1 dimension. And number 2 is something funny happens when you try comparing relationships between rows with so many columns. Almost every data point will look like it's the exact same distance from every other data point. And this makes your comparisons meaningless. And this is where the concept of manifolds becomes really important. On a manifold, which again is a curved surface in space, there's this concept of global and local scale. As you saw before with the rolled paper example, when the data exists on a manifold, we can't use Euclidean distance to measure the distance between points because it doesn't respect the curve of the manifold. But this is within the context of the global scale. The Earth, for example, is round, but if you're standing in a parking lot, it might look flat. So if you're able to zoom into just a few local points or a neighborhood on a manifold, the chaos goes away and suddenly Euclidean distance becomes meaningful again. UMAP forces this local perspective by just worrying about a set number of nearest neighbors to any given point. One thing to clarify here, when I say point, I'm actually referring to data vectors, which you can think of as coordinates. In 2 dimensions, a coordinate of 2, 1 is just 2 over and 1 up. But as your number of dimensions grows, I find it easier to just think of them as each new dimension is like a column in a spreadsheet, and each vector is the row. And whatever vector we're focused on at any given moment is known as the target vector or data point. And for the purposes of UMAP, we're going to find the k nearest neighbors, k just being a value that we pick. And keep in mind, adjusting k up and down will change the type of clusters that form in the UMAP output. We'll use k equals 2 for now. So again, our goal is to zoom into each local data point or vector, find its 2 nearest neighbors, And then UMAP is going to do this really interesting thing where it's going to sort of glue all of those relationships together to approximate the manifold. Hence, uniform manifold approximation, and then projection is more the visualization piece. Now we're going to look at an example, and it's going to be a little bit scary and intimidating at first because it is a math equation, but I promise it didn't make any sense to me when I first looked at it, and now I kind of understand it. So we have our two neighborhoods. We're going to start with neighborhood A, and I know I said I was only going to do 2 points, but it's going to be easier to do 4. So we have our target vector of x of A, and then our nearest neighbor points. And the point of this is we're trying to find how much of a member of A's neighborhood are each of these nearest neighbors. And we're going to assign weights to those. And that'll be clear as to why in a second. And then we're going to do the same with x of B, our other target vector. And we're zooming into different parts of the neighborhood here. And so normally we wouldn't be able to plot these on 2 dimensions, but for the sake of the demo, we're going to pretend that we can. And you can see the x of B, the distances from x of B are greater in these nearest neighbors. And that is just indicating that the data is not linear, which is again one of the problems that UMAP solves. So here's the big scary equation. And all that this is saying is K is the number of nearest neighbors that we're going to compare. And sigma is basically just indicating that we're going to kind of loop through starting at j equals 1 at the first one. We're going to loop through until we hit K number of times, and we're going to sum all of them. And j is just going to act as a placeholder that you'll see here. And so this is getting the exponential of negative max of between 0 and the distance between our target vector, I. We're going to swap out I for A or B, depending on which one we're using, and j, which is again just a placeholder to keep our place in the number of iterations. And then max can be basically if the distance here is greater than 0, then we can kind of ignore the max. And we're just saying the distance between the target vector and whatever other point we're comparing minus something called a Greek symbol called rho of I. And I we're going to again swap out for A or B depending on which one we're looking at. It's just indicating the target vector. And then over sigma of I. And rho is just the nearest neighbor distance. So we're just going to swap it out for that. And then over sigma of I equals log base 2 of K. And the log application here is just to kind of scale the distances so that they are relatively on the same scale, even if we're dealing with big swings in the data as far as the distances. And so what that's going to look like is K equals 4. Again, we're going to use 4 instead of 2 because it's going to make it a little bit easier to visualize. And then the distance of x of A, our target vector, and our nearest neighbor of x of 1 in our neighborhood A that we just looked at is going to be 10. And we're just going to say these are just random numbers just to make the math simple. So they don't really mean anything yet, but I'll show you a real world example in a second. So this will make rho of A equal 10 too, because it's just always the nearest neighbor distance. And then our distance from x of A to x of 2 is going to be 20. Same for x of A to x of 3 and x of A to x of 4. So all of our other points, we're just going to say that their distances are 20. And again, these are just simple numbers to make the concept easy to understand. And then log base 2 of 4 are, again, we're putting the log base 2 of K, so K equals 4. Log base 2 of 4 equals 2. And so that broken down is we're going to go through, so rho of A is just going to equal our nearest neighbor, and so it'll be the exponential of negative max between 10 and 0, so 10, minus 10 over sigma of A is just going to equal, the 10s will cancel out or equal 0, so exponential of 0 over sigma of A, and that is just the exponential of 0 because 0 divided by anything is 0. So the exponential of 0 equals 1. And so rho of A is going to equal 1, and our nearest neighbor is going to equal 1. And then, so x of 1 is 1. And then we're going to plug in our distances for the rest of them as well. So the exponential of negative 20, which is our distance from x of a to x of 2, our second nearest neighbor, minus 10 over sigma of a, plus exponential of negative 20 minus 10 over sigma of a, plus the exponential of negative 20 minus 10 over sigma of a, which is going to simplify down to 1 plus 3 times the exponential of negative 10 over sigma of a equals 2. And equals 2 again is our log base 2 of 4 was equal to 2. And then that could be simplified to the exponential of negative 10 over sigma of a equals 1 over 3. Can be simplified to negative 10 over sigma of a equals the natural log of 1 over 3, because we're canceling out the exponential with the natural log. And then that is going to reduce down to sigma of a equals 10 over 1.098, which is going to approximate to 9.1. And so sigma of a equals 9.1. And if we come back to our original equation here, so sigma, now we have this. And basically what this is going to do is it was derived from the nearest neighbor distances that we looked at. And so it is now kind of a custom made ruler just for this neighborhood, so that we can then get the weights between our target vector and each of these nearest neighbors. And the weights are effectively, you kind of can think about them as how strong of a member of A's neighborhood are each of these. So we're going to continue on. So now we're going to use that custom ruler that we got by going through the process to get sigma of a, and we're going to plug it back in. And so the weight of x of a to the nearest neighbor is always going to be 1, because we're saying x of 1, or the nearest neighbor, is 100% a member of x of a's neighborhood, because it's the nearest one. It has to be. And then the weight between x of a to x of 2 is going to be, we're going to plug in, do the same equation again, but we're going to do it now knowing sigma of a. So the exponential of negative 20 minus 10 over 9.1 is the exponential of negative 1.098, which is approximately 30.33. So, and then because our distances are the same for the other two, because we were making the math simple, those will also be 0.33. And so in effect, we're saying that x of 1 is 100% a neighbor of x of a, being the closest. We're also saying that the other three are each about 33% members of the neighborhood. And so this is kind of the fuzzy weighting that we're giving to the other neighbors. And that is going to, by putting them into a percentage, then we can do comparisons and kind of glue them together in a really interesting way. And so now we're going to do the same for neighborhood B. And for simplicity, we're just going to multiply everything by 10, so we don't really have to go through the math again. So instead of the distances being 10, 20, 20, and 20, we're going to do 100, 200, 200, and 200, which is going to make sigma of B approximately 10 times greater than the sigma of A. So 91 instead of 9.1. And that's going to make the weights roughly the same. So the weight between x of b to x of 1, again, the nearest neighbors, we're always going to say they're 100% a member of the neighborhood. And then the other neighbors are going to have roughly the same membership weights as our neighborhood A, because they're, just scaled 10 times, or times 10. So 0.33, 0.33, and 0.33. So now, if we zoom back out a little bit, we actually see that these neighborhoods are not so far from each other. And x of a, we're saying is 33% a member, or x of 4 is 33% a member of X of A, but actually, in a not so climactic plot twist, X of B's fourth nearest neighbor is actually the same point. So we have these original neighborhoods. So we had neighborhood B and neighborhood A, and we're going to say that it's almost like we're doing this. So neighborhood A and neighborhood B both share one of their nearest neighbors, X of 4. And even though neighborhood B's distances are much more spread out, they're both saying that they are 33%, that X of 4 is 33% a neighbor of each of those target vectors. And so because we were able to convert everything into percentages, now we can kind of say that even though the relative distances are in the custom rulers that we used for each neighborhood, we're able to convert into percentages and therefore give us kind of these standardized ways of measuring membership to each of the target vectors. And then we're going to repeat this actually for every single data point. And then that is going to kind of stitch these neighborhoods together all across the entire data until it forms that manifold that we were talking about earlier. So now a real world example that can hopefully kind of make this a little bit more clear. So let's compare day-to-day price changes in airline flights, and these are hypotheticals, but let's say the X of A is a random Tuesday flight, and its day-to-day change, so Monday to Tuesday, is going to be maybe a $10 change. There's not really a reason for the price to shoot up day over day. X of 2 might be another point in our data, might be a random Wednesday, and that day-to-day change might be only $15. Random Thursday, maybe only $25. A standard Friday, maybe a little more expensive than a Thursday, so $45. A 3-day weekend, maybe $80, because that's a more desired time for people to be flying. The start of summer, even more. Let's put that at $135. And then Thanksgiving is going to be quite a bit more than the day before, so $220. And then the price is going to fluctuate quite a bit on Christmas Eve, so $330. So we're going to say that X of A is the random Tuesday, and X of B is the start of summer. So the X of A, the $10 day-to-day change, X of 2 is only $15 away, or is only $15, which is only a $5 difference from X of A. And this is kind of our distance measure that we were talking about earlier. X of 3, $25, only a $15 difference. X of 4, $45, only a $35 difference. X of B, $135 day-to-day change. Again, it's a little bit more of a desired time to fly. X of 5 is the nearest neighbor at $80, which is $55 away. X of 7 is a $220 day-to-day change at $85 away from X of B. And then the third nearest neighbor is X of 4 at $45, which is $90 away from X of B, but that's its third nearest neighbor. So X of 4 is the third nearest neighbor to both X of A and X of B, and we're able to, we would be able to go through UMAP and have sort of a similar, run the math and get similar weighting that would put these each roughly, similarly distant to each other and similarly percentage members of each other. Okay, so now what we're going to do is we're going to look at a real-world example of UMAP. And for that, we're going to look at Microsoft search query results through Bing. And we're going to take this complex text data, which is high dimensional by nature, and we're going to boil it down using UMAP to just 2 dimensions. So to do that, we're going to bring in we're going to install some data sets and some libraries like Sentence Transformer, and then bring in UMAP, obviously, and then we're going to bring in some things for plotting the data. So install those, and then we're going to import them and load the data set. And then we're going to append the data set into an array and take a random sample of 5,000. And then we're going to load our sentence transformer, which this is a stripped down version of a sentence transformer or an encoder called BERT, which was developed by Google. This is a version that was developed, a distilled version that was smaller and developed by Microsoft, or I think it was developed by Microsoft. And we're basically going to convert, this is going to be used to convert our raw text data into what are called vector embeddings, which is just an array of numbers of 384 separate dimensions representing each sentence. And then we're going to load it in, and then we're going to build the UMAP reducer. So this is just the UMAP model. We're instantiating it. It's using 15. So in our example, we used k equals 4. We're using k equals 15. So this is the number of neighbors that we're going to look at for the relationships. And then we're going to run it and transform the data to take our original BERT embeddings and create UMAP embeddings. So this is the part where we're distilling down the embeddings of 384 dimensions down to just 2 dimensions. Now we have a new array of simplified embeddings. And then we're going to use a k-means clustering algorithm to try to find 10 distinct clusters from that 2D map that UMAP has just built us. It's just going to try to draw the boundaries. And so that's what this is doing. It's fitting and predicting to create the cluster labels. So now we've got our normal embeddings, which is the representations, the complex representations of 384 dimensions for all of our sentences. We've got the UMAP embeddings, which is the simplified 2D version. And then we've got our cluster labels for each embedding. And I'll show you how we kind of combine all of those for the plot or the chart that we're going to build. And so this is just a line wrapping function just to cut off words if they overrun the width of the chart. And then here is our data frame. We're putting the 0 index of the UMAP embeddings in the x-axis, and then the 1 index in the y. And then we're getting the cluster labels and mapping those, and then the text as well. And then we're going to config the chart. It's going to be a scatter chart, and then the final output is this. And so again, what we've done is we've taken complex text data, we've converted it into embeddings, we've used UMAP to boil those embeddings from 384 dimensions down to just 2, and then we've plotted it all out, and let's see what we've got here. So this yellow cluster at the top looks like it has to do with language, maybe, compared to this pink cluster over here, which looks like it has to do with preheating the oven. It looks like it's mostly about cooking, so cooking results, versus like this darker green looks like it's about taking medication or questions about medication, versus this looks like it might be about illnesses, so it makes sense that it's close to the medication section. So you can kind of see that hopefully this gets your wheels turning about just what you're able to do with UMAP. We've taken some really complex text data, and now we've made sense of it in a really short amount of time, so hopefully you can find real world applications for this to be able to help you in your day-to-day. Think about what we just did. This might have taken Callimachus and the Alexandrian library staff years to organize, and we did it in a matter of seconds. But regardless of the amount of time spent, both the stories of the Alexandrian team and the UMAP team act as reminders that when a problem becomes overwhelming, reducing dimensions is almost always a helpful first step. And I have a theory that insight is going to be one of the keys in solving AI's hallucination problem, and potentially even its economics problem, which is a topic for another video. Thanks for watching. Have a great week.